Strategic review of section 11 electromagnetics. As I mentioned a couple of times already, electromagnetics, for me at least, was the most difficult subject that I ever took in my undergraduate and graduate engineering coursework. The reason is that electromagnetics, very similar to what you guys are finding, has a requirement. It expects that you're going to visualize, you're going to sketch, right, in three-dimensional. We typically don't, well, we live in three-dimensional, but we typically don't sketch things out in 3 dimensions, right? Because the paper itself is a 2-dimensional space. But you need to do this sketching. I'll jump just to the final point right up front. If you don't do sketching and visualization, you're setting yourself up for failure for any question that is between medium and hard level difficulty. And the easiest way to make any question medium to hard level difficulty in the context of electromagnetics is just throw in some element of sketching and visualization, right? And that will neutralize your arsenal when it comes to the formulas, the plug and check approach that you might be walking into the exam with. So whenever in the program, I give you an opportunity to sort of test you on the quizzes, mini exams, homework assignment problems with sketching, please take your time and sketch things out. Another reason that I found in my undergraduate and graduate studies electromagnetics to be challenging was the fact that it includes advanced mathematics. So the vector calculus that we came across in Maxwell equations, in my graduate course, we were using it quite extensively. Even in the undergraduate coursework, right? Some of these integrals, first integral, second integral, third integral, so they can become very challenging. Thankfully, in the FE exam, though, with the reference handbook, the formulas that they've provided us are still fairly easy and straightforward. When you have a single line integral, that's basically along one of the dimensions, x, y, or z, right? When you have 2 integrals, that's basically an integration in terms of area. When you have 3 integrals, that's basically an integration in terms of volume. So these are fundamental concepts. Understand the formula with the units of measurement. Direction is super important. And again, this also comes back to this. We did several practice problems involving the force on charge 2 due to charge 1 and so on. Unit vectors come into play, and we need to handle them very carefully. So students sometimes mix the unit vectors polarity direction with the polarity of the charge. They are two separate things, guys. Okay, if a charge is negative, that means, so let me give you an example. If I have a negative Q charge, this negative is associated with this charge. But if I have a direction of, let's say, negative X, okay, direction of negative X, I, right, plus Y, J, for example, plus Z, K. This negative that you are seeing over here is because of the direction of the unit vector. Now, what will be the impact? This is also a negative. This is also a negative, right? So along the x-axis, the net effect would be positive. So you need to be very clear about the polarity that is being introduced because of the charge itself and the polarity that is being introduced by the unit vector or the direction. And these things can become very convoluted. Again, it comes down to your understanding of the spatial arrangements, which is fundamental. Work done by a charge or on a charge. So we've done that, done these examples several times, right? So start with the basic equation and then build it up. And energy stored in an electric field contains 3 integrals, which basically translate into a volume. So as much as possible, try and condense the integral of whatever is being integrated into a final product. So for example, the integral of E and dl, right? So we have this integral. We know that that is equal to delta V, correct? When we have the triple integrals for the energy stored, we know that this is a volumetric integral, right? Integration. And we can use the volume of wherever the space we are integrating it as a direct conversion. Okay, so you need to be smart about that, and we have several practice problems. So that is electrostatics, magnetostatics that deals with stationary charges and magnetic fields, right? Then we have electrodynamics where things are in action, and that's where Maxwell equations come into play. Wave propagation, we basically just touched the tip of the iceberg. Schrodinger's equation, if you take advanced graduate courses, you'll have to work through that. And that's where vector calculus is in all its glory, right? It's very, very complicated, and again, requires a lot of visualization for in the context of the FE electrical and computer exam, they've kept it fairly simple. But Maxwell's equation, the way that I've tried to explain you guys in the on-demand in the live training is through the application. From an application standpoint, using the Gauss's law, Faraday's law, and Ampere's law. To be quite honest, I mean, the way I explained it was that we looked at Gauss's law, right? And then from there, we created the integral. You guys remember in the live training, right? Equation for integration, equation for the vector calculus. So if you take that approach, it's going to stay with you much longer and you'll be able to make more sense out of it, okay? So try and practice both the integral and the vector forms. I typically find, as I mentioned in the program, that the vector forms are much more easier to deal with as compared to the integral forms. And that's been the experience of most of my students as well. And at a very fundamental level, these two quantities that we come across, curl and divergence of a vector field, please practice them, okay? And we have plenty of practice problems in the quizzes, especially divergence, because this is a cross product. And you don't have to memorize any formula. It's all given in the reference handbook, not as explicitly as you'd like and not within electrical and computer engineering tab. It's given in the math tab. So please go through that and make sure you do a little bit of a practice, and that will be more than enough. So that's electrodynamics. And the final topic within electromagnetics is fairly easy, lossless transmission line. When it comes to P power, guys, we're going to deal with lossy transmission lines. We're actually going to be dealing with 3 different models of transmission line. We'll have a short model, a medium model, and a long model of a transmission line. So what you see over here is really, again, tip of the iceberg, intro level stuff. And for the most part, it's plug and chug. The things that you need to be careful with, which I emphasized in the live training as well, is that when we are dealing with the reflection coefficient, okay, it is a complex quantity. So it can have a plus bj, right? It may not always have, but it is complex and it can have an imaginary component. When we're dealing with standing wave ratios, so again, reflection coefficient is built up of your characteristic impedance and the load impedance and whatnot, but it can have an angle, it can have a real and a complex component. Standing wave ratio is magnitude. Students confuse them. Sometimes even for reflection coefficient, they're like, okay, just grab the magnitude and run away with that. Please don't make that mistake. I emphasize that in the live training as well. And then the equations for input impedance and velocity of propagation, frequency, characteristic impedance, those are all plug and chug, but you still need to be mindful of what you are doing. So all in all, electromagnetics, I started out by saying that it was one of the most difficult subjects that I took in my undergraduate and graduate courses. In the context of the FE electrical and computer exam, they're more difficult topics than this, and primarily because of the fact that they've taken a little bit of an easier approach, right? They have just provided you half a page of reference material on Maxwell's equations, and then roughly half a page or roughly a full page on transmission lines and so on. So overall, it's not too bad. And the one thing that I want to emphasize before I let you go is visualization and the importance of sketching. If you can do that during your exam preparation, you're going to be very, very, very comfortable during the exam as well. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, StudyforFE.com.